Make sure to change your answer if you changed your mind. Polling is still open. Fantastic. We went from almost 50-50 to 50-50. All right, so what's going on? There's one best answer to this question. There are not two best answers to this question. So let's think through how we choose which one. So if we had one word, one phrase to describe how we choose one over the other, what would that phrase be? Kevin? Formal charge. Okay, so go ahead if you haven't already and determine the formal charge of every atom in all three of those structures. Write it down on your paper. You have these images on your question number 1 on your worksheet as well. Nope. Everything you need for today should be on today's worksheet. So there are 2 stacks of them in the back, and I have a couple more. It also is the last question on that. How many do you need? 50, can you pass these back? Raise your hand if you don't have one of today's worksheets. Can you pass these back in that direction towards Moab? You get one for today? There might not be any right there. All right. Raise your hand if you need another 20, 30 seconds to complete the formal charges. All right. You have 30 seconds. And at 11.
11 at night? Oh.
No, I'll be All right, can I have 3 volunteers? 1 for each molecule to read left to right with the 3 formal charges for each atom. 1 at a time, 1 volunteer. Love, do you want to start us off? Great. Next volunteer. Sarah?
-1, +1, 0.
Great. And the last structure, Ruby?
-2, +1, +1.
Okay. Which one can we automatically discount? All right, so this one we have more non-zero charges because there's 3 non-zero charges, and those charges, those formal charges, are higher in number and magnitude. So we can't have either one of those. So then we have these 2 options here. Who wants to argue for one or the other? Which one do we choose and why? Josh?
Mine's a little simpler. Every time I've ever dealt with nitrogen, it's always been triple bonds to each other.
Okay, so you like the idea of having a nitrogen with a triple bond? Okay.
Well, I actually know the Lewis structure already for this. It's A because and the reason for that is because it's kind of because of what he was saying. Because the energetics of forming nitrous oxide, is more apt to that rather than more apt to A rather than B.
Okay, so there's a term we haven't really used in this class, electronegativity. And that's one of the main things we're going to use to describe why the left structure is more likely to form than the central structure. So the term electronegativity relates to if we have two atoms that are bonded together, they're sharing electrons with each other, which one is more likely to pull the electrons towards itself? What is the pull of those electrons, one side versus the other? The most electronegative atom on the whole periodic table is fluorine. That one has the strongest pull of electrons. Can anyone think of why that one would pull electrons towards itself more than any others?
It wants to get that one more electron.
Okay, the stability of getting that one more instead of wanting. We can say, whichever phrase is fine. It becomes much more stable by gaining one more electron or having that closer to itself. And so we're thinking about how close we are to the right side. What's also different about fluorine compared to, so you can say the same thing about chlorine or bromine or iodine. Why is fluorine more electronegative than either of those two? Both?
Because it has less shells.
Okay, it has less shells, true. And? 50?
It has higher ionization energy.
It has a higher ionization energy because
the electrons don't shield the nucleus.
Smaller.
it's smaller. Fantastic. It's one of the smallest elements in the periodic table, aside from the noble gases, which already have a full set of valence electrons. So it's really small. That electron is going to bring it to a state where there's more attraction. So what we want to say is that fluorine is the most electronegative element in the periodic table. Where do you think the trends are then? Do you think as we go up or down, we're going to have an increase in electronegativity? Up is more electronegative, and to the right. It's always easiest to say to pinpoint the one that has the highest electronegativity, and usually the trends go backwards from there. Okay, so if we look at oxygen versus nitrogen, which one of those two is more electronegative?
Oxygen.
And that is the one that if we have to put a formal charge on one, we're going to put a formal charge on the one that has a higher electronegativity. All right, we're not always going to put a negative charge on oxygen, don't get me wrong. But if we have to, all of our low structures can only draw with a formal charge on either nitrogen or on oxygen. We're going to put the negative formal charge on the one that's more electronegative. And then nitrogen is more capable of handling a positive charge than oxygen. Okay? So with all that said, that first low structure is the best. Triple bonds are also nice for nitrogen, but it only has 4 bonds, so it's going to be positively charged, which isn't what you see as a normal. Okay? So then let's go ahead and do the next couple of questions. So I want to know if you guys are getting comfortable with the term steric number. I think the question on your paper says determine the steric number for every single atom. And we're referring to structure A now, because that's what we determined was the best structure. So in structure A, I want to know what the steric number is for the terminal nitrogen. What does terminal mean?
Ending.
The end, right? It's the last stop on the train. It's the terminus of the train. So go ahead and click in what the steric number is for the terminal nitrogen in N2O. Make sure to determine all the others as well in that nitrogen. You can practice on the other molecules as well.
Oh.
Couple more seconds. This should be a pretty quick answer. Make sure your answer is submitted. Closing out. All right, we have 2 main answers. Is it 1, 2, or 4? See a mix. Someone feel very confidently about their answer who hasn't spoken yet? Want to share their thought process in it? Yes.
The start number
How do you define it?
is the number of lone pairs plus the number of bonding domains.
Domains. That's a big word. What does that mean?
It's not the number of bonds, it's
Correct.
the number of times it bonds.
Absolutely. So this nitrogen has 1 lone pair, that's 1 steric group, and it has a triple bond, that's 1 steric group. So if you think back to the lab that you guys did last week or are doing today, you guys will get to see if we add more domains around the central atom, the number of domains is what affects the electron pair geometry. And so I want us thinking about how many domains there are and what kind of domains they are. And so we'll go back to the AXE notation in a second, which takes that number of 2 for the steric number and breaks it down into, well, are both of them bonding? Is one bonding and one lone pairs, or are both lone pairs? So if we then look at the next nitrogen, the central nitrogen, go ahead and think about that. Actually, we'll do the AXE notation first. We'll try to click this in. All right, that nitrogen that we just decided has a steric number of 2. What is going to be the AXE notation? This is the last thing we did in class on Friday. It was a little rushed. Talk to your neighbor, try to figure out what we're going to do for the AXE notation for that nitrogen. To make sure we're all kind of on the same page, it's always going to be A and then X and E if it has both bonding and non-bonding. Which one is bonding? Which one's non-bonding? X is the bonding domains. E is the non-bonding domains. And we don't have subscripts in your clicker, so it'll just be A, X something, E something. What do we do if there's no lone pairs? Do we include E if there's no lone pairs? Nope. Wouldn't include it. So have you guys got a chance to submit a response of some sort? We're going to be doing a lot of these today. So if you're not completely comfortable, that's fine. We'll be giving you a lot of practice. So can we get a new voice to share what they would put for the AXE notation for that nitrogen? New voice, new voice. New voice, please. Savannah. Savannah, right?
Yep. That's what I did.
Okay. Take a guess.
I think it's I think it's 2 bonds. I haven't done this lab yet.
That's fine.
It's 2.
We actually don't do this in the lab. This is
Oh, okay.
something that we're adding on to what's happening in the lab.
Yeah.
So how many, let's ask this question. How many bonding domains are there on that N nitrogen?
I think it's 2.
Bonding domains? How many areas of bonds are there on this nitrogen? This isn't bonding. This is just lone pair, so these are non-bonding. And then this is bonding.
1.
And then non-bonding? How does 1 sound to you? Yeah. So we wouldn't actually write AX1E1. We would write AXE. Because we have one bonding domain, it's the triple bond connected to this nitrogen. And we have one lone pair that's non-bonding that's on the other side. Okay, so let's go through that same process, but let's do it this time with the central nitrogen in structure A. Go ahead and click in what the AXE notation is for the central nitrogen. You might want to start like we did, what's the steric number, and then what are those 2 steric numbers composed of? Thank you. All right, 20 more seconds. I hear from a new voice. What did you answer for the AXE notation for that central nitrogen in structure A? Yeah, Mohan?
AX2.
Why'd you decide AX2?
Because it has 2 bonding domains.
Great. And
No lone pairs, so I didn't include E.
great. So we have one bonding domain on the left, that's a triple bond. One on the right, that's a single bond, AX2, that's it. You don't have to include the E because there are no lone pairs. All right, looks like we had a large percentage of that, but we had some people with putting the E there. So the E's and the X's are only there if we have one or more of them. So try to make it as simple as you can. All right, so our learning objectives for today is all about drawing Lewis structures and interpreting the Lewis structures and using that to think about the shape of the molecule. So building off of the lab that you guys are doing either today or last week. We're also talking about naming polyatomic ions. I gave you that table last week, 2.5, I think it was, from your book. We're going to be using those today. I'm expecting you guys to know them all today. And in doing that, we're going to determine the steric number in the AXE group. How do those two numbers at the bottom of the X and the E relate back to the steric number? Sorry, who's saying that? I hear Mohammed. Sorry. Great. So hopefully you're noticing that the steric number is we have 3 domains of electrons, 2 of which are bonding and 1 is non-bonding. They always have to add up to each other. So that's why I put them in the same line, is because they're absolutely related to each other. One is more blunt, just being like, there's 3 things around the central atom. And then we can determine the electron pair geometry. But if we want to know the molecular shape, we have to know how many of those are bonding and how many are non-bonding. All right, we're working on calculating formal charge. We're practicing that for individual atoms, an entire polyatomic ion. We'll be doing lots of that today. Identifying when more than one structure is possible, which we call resonance structures, and then determining which resonance structures are most accurate. Sometimes there is one. And then we're going to be talking about what that means about bond length, strength, and sometimes averages. All right. We're going to do an organic molecule. I want you to go ahead and draw the Lewis dot structure for propane. And you have the formula for propane there. There is a bit of information hidden in that formula. It kind of starts to show you what it might look like. So you can work with your neighbors. I think this is question 5. Wow, we're cruising today.
Oh, no, it will look bad. Yeah.
Alright, it looks like we have a lot of structures drawn. What information is hidden in the formula, the way that it's written? Logan.
So, like, this atom shows the hydrogen there. So, like, when you draw your structure, you actually started telling you what's going to bond to each one.
Yeah, it kind of shows you the skeleton as you go along. And so it implies that carbons are the skeleton. How many carbons long is propane? 3. All right, so the word prop in chemistry means 3. So you'll be seeing, we'll be doing some more nomenclature as we go along. Nomenclature is a fancy word for naming of things. So we have 3 carbons, and I totally lied because I said Lewis dot structure, right? And that's not the dot structure. So Lewis dot structure is just with the actual dots. I want to show how much of a pain it is to do this. Is really the reason I'm doing it. Okay? And then, like Logan pointed out, the structure the way it is there, it's a little bit expanded. We could have just said C3H8, and then we don't have any structural information at all. So the way this is written tells us that it's strung out, that we have 3 hydrogens on each of the first 2 carbons, or the N carbons, 2 on the central carbons. So the dots are shared. This one maybe came from the right carbon. This one came from the left carbon. So if you do them as a line between them, it doesn't really show that one came from each atom. So when I show a Lewis dot structure, I like to show the electrons as being equal distant between the two atoms, because the reason they're there is to help kind of stabilize the other atom to get closer to the octet. What trend do we see with carbon? 4 what? We always see 4 bonds with carbon. There are some really rare exceptions that we might see this year, and if you go into organic chemistry, there's going to be more exceptions. Everything that we're talking about in this class, for the most part, is trends. And there's always exceptions to trends, but we'll be trying to hold on to those trends so we can kind of make predictions as much as we can. All right, so every carbon has 4 bonds around it. That sounds good. Does everyone have a full octet? Or a duet, right? Hydrogen is always going to have a duet. We have the carbons with octets. Everything looks good. Could you predict the electron pair geometry and molecular shape from the drawing here? We should be thinking about that when we go into lab today. What does electron pair geometry mean? How does that relate to molecular shape? Are they the same? When are they different? And then how do we draw this as a line structure? Have you guys ever done line structures before? So in organic chemistry, organic means carbon containing. That's what I have my PhD in. I spent a lot of time drawing structures. Do you think I want to draw this level of detail every time I draw a chemical structure?
You draw like a line, right?
Did you just skip the C?
So if there's ever a carbon, that's the beginning of a line. If we don't draw 4 bonds, for instance, how many carbons do I have on that line?
2.
2. 1 at the start, 1 at the end. How many hydrogens are implied?
3.
Why 6, Kayla? So basically each one of these is a carbon. They only have 1 bond each right now. But because I'm an organic chemist, I'm going to draw this until I'm blue in the face. I don't want to do that. So if I don't draw 4 bonds, there's lots of hydrogens there. You can count up how many. Okay? Is this the right line structure for this molecule?
No.
What do I need to do? 1 more line. This is propane. As is this. Which one's easier to draw? Which one has more information? I would say this one actually has more information. This one gives me some idea about shape as well. And this one doesn't.
So how do you know it's supposed to be slanted?
So every time we're going to draw lines, however many lines we draw, how many carbons do I have down here? 1, 2, 3, 4, 5, 6, 7. Every time a line starts, stops, or changes directions, it's a carbon. Any carbon that doesn't have 4 bonds already drawn to it has hydrogens, and we can count how many hydrogens. That's what skeletal structures or line structures really are. And we're going to use those a lot in this class. The reason...
molecule there is in heptane.
So why do we draw them bent at a certain angle? And what angle is that? There's no lone pairs. It's about 109.5. Why? Because each one of these carbons, if I wanted to draw in all the bonds, has a steric number of 4. We can keep going, right? Steric number of 4, molecular shape is tetrahedral. If it's tetrahedral, molecular shape, then that means it has a 109.5 bonding. So these are maybe I drew them closer to 120. I don't know. It doesn't matter. But by showing that it's not in a straight line, we show that there is different angles that we have for those atoms and the connections between them. The thing we can keep in mind, and the thing that the people who are going to lab today can do that the rest of us might not get the chance to do, is when we build a molecule, think about how those single bonds rotate. They spin completely freely. So this is one way to draw the molecule, and propane as well. There's nothing to say we couldn't draw propane like that, where those bonds are spinning around each other. We could also draw, instead of continuing our lines like this, we could draw, and this is the same as this because those single bonds are freely rotating. We'll talk about the rigidity of double bonds and triple bonds as we get further into this week. So we're just representing, we're counting how many times a line starts, changes directions or stops, that's how many carbons. And then we can get a lot more information from there with the hydrogens and some about the shape. All right. So we have multiple ways of drawing this. We could also have drawn the first structure instead of the Lewis dot structure as a regular Lewis structure and had lines instead of the dots. That would also be fine. That's called a Lewis structure instead of a Lewis dot structure. So I think we'll pass on this question just because some people in the class haven't gotten to this yet. But for every time I show you a molecule in this class, you should be thinking, every atom, what's a steric number? What's AXE? What's the molecular shape? What's the electron pair geometry? And we're going to be talking about what the hybridization is by the end of this week. Okay? So you should be able to pick any atom and be able to answer a question like this or about any of the other topics we discuss. By the end of this week, I hope that you can look at a molecule and know a ton of information about it just by something drawn on the paper or something you draw on the paper from a formula. All right. Go ahead and draw the Lewis structure for carbonate. You guys all memorize them, right?
Dots.
Just a regular Lewis structure is fine. Is anyone lost with the formula? You're welcome to look up formulas today for polyatomic ions. As we keep going through the semester, I want you to need to look them up less and less. On the exams, you need to know them.
Where is it? Is that in our book?
Table 2.5, I think.
Seems like a bad idea.
Everything I do, I need to make sure that I can justify changing it in class, right? You see a score. Because you didn't have a score, I can do that. Because then you would know if everyone in the class is like, well, I don't know too, because I didn't get high scores. You know what I mean? It's still a very good score. You're doing well. Raise your hand if you'd like a little bit of input. Sam and I can come around and help. And I would highly advise doing S equals N minus H to start.
So what was it? So everybody right the total that it needs, so all of them need.
Yeah, I'm trying to figure out like
So valence electrons, right? So the ones for all of these, and then you
what valence electrons these are. So what's the number?
well, that's what it is. So N is 8 times. So N is the total number it needs to go.
Well, in, you know, I would say minus extra electrons. That's not the starting equals 2.
Those are the valence.
Yeah, those are the number of valence.
Yes.
This is
So
it.
that's another thing. Well,
Then what's
okay.
in?
N is the number of octets for all of these three. And so that's going to give you how many electrons you need to bond. And so
Yeah, but what's in?
by making
Octet would do like,
yeah, so it's a different way to do it. Like,
then But, you know, I this is also
All right. So today's day one of you knowing your polyatomic ions, and hopefully you'll see that if you can't pull them right out of your memory, it does slow us down. So kind of that's an example of when we move forward. The more quickly we all memorize them, the more quickly you can actually have conversations about content as opposed to what that name means. So what is the formula for carbonate? All right, CO3 2 minus. And I saw a couple people not quite sure what to do with that 2 minus when we're doing S equals N minus H. So if we do S equals N minus H to figure out how many bonds we're going to have in this molecule, what is our N?
The number you have of valence electrons.
Right, how many do we have for this one? 32, because we have 4 atoms, all of them would have octets, so that's 4 times 8 is 32. We're going to subtract H. And so if we do H, that's how many valence electrons we have. We have 4 from carbon. We have 6 from each of the 3 oxygens, so that's 22. What did I forget? Negative 2. What does the negative 2 tell us? It means that that molecule has all the valence electrons from all the atoms and 2 more, because each electron is negatively charged. So that number should actually be 24. That's how we use the formal charge in determining the structure of a molecule. Okay? So then the difference between those is 8. How many bonds do we have? Divided by 2 is 4 bonds. So we're going to go ahead and draw our carbon. We can easily draw 3 bonds. Where do we put our 4th bond? Does it matter which one? Does anyone look better than the others right now?
No.
All right, and that's a bell that should go off in your head. There's more than one structure. So this is where resonance structures come from. I'm going to pick one. Okay? That is the one that I picked. I'm going to pick the bottom right. But there might be equally valid structures drawing that double bond to any of the other locations. And there is 0 preference in this particular example. There's nothing else attached to the other places. It's completely wide open. So that should be sitting in our heads like something that's standing out we're going to have to do something with. All right, and then we say, well, how many more electrons? We've only done 4 bonds with 8 electrons. How many more electrons do we have left out of all those valence electrons? How many more electrons do we have in this structure? We had a total of 24. We've used 8 of them, so we still have 16 electrons left. So we can go ahead and add those electrons. What do we do with the last 4? Okay, so those oxygens didn't have octets. You're going to always, pretty much in this class, you're always going to find oxygen either with 1 bond and 6 electrons, like this, or you're going to find it with 2 bonds and 2 lone pairs.
What about carbon monoxide?
There's exceptions, for the most part. All right, so we have our structure drawn, one example of a structure. Are we done?
No.
What do we still need to do? Can I get a new volunteer? New voices, new voices. Kayla. Okay, so there we can do this. We can draw a bracket around it, and then what do we do? Okay, we can say 2 minus. This is kind of a generic way of saying, well, this structure has 2 more electrons than the typical valence electrons for all those atoms. But I want to be more specific. So how do we be more specific in that? Gail? Okay, we're going to get there in a second. Joey? Yeah, I'd love to see the individual formal charge. Where is it? So where did you put the formal charges?
So bottom left, -1, top -1, central atom is 0, and then bottom right 0.
Great. And when we start doing this more and more, we'll probably not include the zeros for the most part. We'll specify whether there's a positive or a negative. But it's good that we always go through and check to make sure, because if there is a -1 overall charge, it doesn't mean if we find a -1 that there aren't any other charges. So nitrate's a really good example of that. Nitrate has 2 negatives and a positive. That overall bracket tells you the sum of all the formal charges. Okay, so we have a structure for carbonate. What should we be thinking about now? Not going to resonance structures yet. Now that we have a drawing, what should we be thinking about? Anytime we have a Lewis structure drawing. The shape of it, the electron pair geometry, the molecular shape, steric number of each atom, the AXE notation. All those things we should be thinking about and be able to answer. All right, so we have the Lewis dot structure, we have the Lewis structure, and then we already have the formal charges. We went through that. I want you to determine how many resonance structures you think we can draw for carbonate. Go ahead and click in your response.
Is that including the first one, or is it like?
Yeah, resonance includes all of the possible ones. It's not how many alternate, it's only how many total. Couple more seconds. Is the number of bonds that makes the molecular shape? Have you had lab yet? Have you done the lab yet? Okay. Bring that question with you to lab. All right, closing out. All right. We had a majority answer that we have 3 resonance structures. Why did we say 3? Can I have a new voice? Why did we say 3? Savannah?
You can put the double bond on each of the oxygens.
Great. And we had 3 different places that we could have put that double bond. I chose the middle structure to draw for my first one. You could have drawn it to the top, or you could have drawn it to the bottom left. Any of those 3 structures would have been fine. I saw a couple people starting to draw their structures with this kind of layout of the atoms. Why is that important? Instead of doing it like a T. Know it?
It gives you a better idea of the electron pair geometry.
Great. So we're thinking about if we have 3 domains of electrons, they're going to want to be as far away from each other as possible. That's what Vesper talks about. And as far away as they can get from each other is trigonal planar stretched out like that. So if you ever want to practice this and you're not quite sure why, bring up that simulation that we did in lab, the PhET simulation, and then make the molecule and see where those individual domains go. All right, so we have these 3 Lewis structures. You guys notice the arrows for resonance structures? Are they full arrows in both directions? They are absolutely not. This is not a reaction. This molecule in the middle bounces back and forth and is some version of all 3 of those. And actually, we're going to be thinking about it more as an average of all 3 of those structures. So it's going to hurt your head a little bit. So what would you say to this question then? If we were to look at one carbonate molecule in nature, what would you find as far as those structures? Question 8 on your worksheet as well. Check with your neighbors, see if they agree with you. We have 2 to 1 as far as our responses. There is a lot of utility in drawing Lewis structures, but one of the worst things about Lewis structures is that we can't draw what an average looks like. So we have to draw all 3 structures and say that this is an average. So anytime we have a Lewis structure, it's going to be an average of all the different resonance structures that we can have. So C is our best answer for this question. Yeah, Joe.
But you're not going to find an average. You're going to find all 3 of them randomly equally defined with 1 atom.
So our representation, our drawing, is very different from what we actually see. If you go out in nature and you find a carbonate ion, you can look at how long and how strong each one of those 3 bonds, and they're all equally long and equally strong. That's an average of those 3
You can't
structures.
measure like one carbonate in one area. You know, like you can't measure it like in one part of the resonance structure. You just can't do that.
Exactly. All right, so let's think about salts for a second. Should we... Let's do this as a numeric question. If we have that carbonate, how many sodium ions would we need in order to make a neutral salt? Go ahead and click in your response. All right, 10 more seconds. All right, closing out. Our majority answer by far is we would have 2 sodium ions. Tyler, why is that? Great, so we want to identify what the charge is that's likely to come from any metal. So we know that sodium is +1 because it's on the far left. It's an alkali metal. It has a +1 charge because it has 1 valence electron that it can give up. So we have Na+, and then we have some number of carbonates. The statement up top here is true for any time we find a salt, the formula of a salt. The total of the charges is always going to have to be 0. So then we would have, if we have 2 sodium ions and 1 carbonate, that would be a neutral sodium carbonate. All right. Did I need to tell you that in the name? By knowing it's sodium, knowing something about the periodic table, we know that it's a +1 charge. We know their carbonate is a 2-. We can figure out what the ratio is in order to find that neutral salt. There's some elements, some transition metals, where I do have to tell you something about it in order for you to know how many are paired with each other.
Like copper.
Like copper, like iron. What about calcium? Go ahead and click in that answer. How many calcium ions would you need to find with carbonate to make calcium carbonate? Limestone. Because you don't need it. So that's usually organic compound. When you're using a metal that's not a salt, then because you know it's probably going to be
That's not the same thing.
All right. Our major answer in this case is 1 to 1. So why would we need 1 calcium atom in order to make a neutral salt? Great. So calcium is always found as a 2+ if it's an ion. Carbonate 2 minus. So calcium carbonate with 1 to 1 is a neutral salt. All right, are we going to do a lightning round here? Let's do a lightning round. Ready?
Yes.
And go. Potassium carbonate, which is the correct formula? Closing out. Bam. All right. Justification. Group 1 metal with carbonate, we know the charge based on where the metal is in the periodic table, so we can figure that out. What about magnesium lithium? Which of these options is best?
Wait, that's not a salt.
Why is this a terrible formula to write? It would be 2 cations. We can't make a salt with 2 cations, okay? Last thing I want to leave you guys with is there are a couple of opportunities for you to practice drawing with phosphorus and sulfur as a central atom. But let's do this question to make sure your brains hurt on the way out of class. Thinking about length and strength of bonds, there's a statement up top. Answer the question. Click in your answer. Are the single bonds longer? The double bond longer? Are they all the same length? Final answers. We're not quite sure. Why?
It doesn't make sense.
It's an average. What about the strength? Double bonds are stronger than single bonds. What about the strength?
They're all the same.
They're all the same strength because they're all an average when you find them in nature. Okay? We'll build off of that next week or next class. I will send an announcement out with something that will be useful for your lab this week. Thanks everyone for your patience. Oh, I have office hours today right after class in E-Task 125, and I have office hours at 4 o'clock in 273 Science Lab.